There, now I'm recording. Any questions? Questions about the class? Everyone's excited? Calculus 1. Most of you needed Calculus 2, which means you probably need Cal 3. How many of you are engineering majors or something like that? Okay. All right. Biology? Okay. So biology, it's like Cal 1 is usually the requirement, right? All right, so let me just talk just generally what my goal here is for you, all right? I'm trying to help you become a problem solver, right? It's not necessarily giving you a test and saying, oh, can you basically repeat the things that have been shown to you? It's more of, can you solve problem? Can you put your ideas together, form an approach, an attack of a problem, and then figure it out? Because that's the greatest skill that you can leave college with, especially going on to engineering or even biology, whatever it is being comfortable with problems that normally would make most people uncomfortable. And so hopefully you can become an independent learner and resourceful, meaning that maybe you'll make some friends in the class, you'll get together, you'll study, help each other out. I think that's another good skill to pick up. What is Calculus 1 about? Anybody heard anything about Cal 1, like what it is, or no? No? No one's heard anything about calculus? Have y'all heard it's hard? Have y'all heard it's easy? What have y'all heard? What's the story? That's hard? No? Anyone heard anything else? Y'all are going to be real quiet. Y'all don't want to talk too much. Okay. Well, I have my opinion on calculus. I think that the ideas of calculus aren't that difficult. The concepts. What makes calculus difficult is you've got to be really good at algebra. You've got to be really good at algebra. It's like algebra on steroids. I'll give you a real quick example, okay? This is more of, what do you call a question where you don't answer it? It's just to think, rhetorical question, right? My question, can you factor that? Factor that. Okay, so you're thinking, yes, okay, I feel good about that. Do you feel good about that? Rhetorical question, I don't want an answer. That would be what I meant, factor it, difference of squares. So again, asking yourself, how comfortable are you with that? Okay, how about this? Can you factor that? No? Okay, how about this? What would happen if I multiplied this times this? What would I get? I get x, right? What happens if I go here times here? I get negative 2 root x, and then here to here, positive 2 root x, right? Those will cancel each other out. And then you do the last multiplication, you get root 2 times negative root 2, which would give you what? Negative 2. So that is the factorization of x minus 2, right? But you've never seen it that way, right? Because it doesn't look like a difference of squares. You would not think difference of squares. That's the type of algebra that this class requires. That, not necessarily that you've seen that before, but when I show it to you, you go, holy shit, that's a whole new world of things that I now can do that I didn't necessarily think about before. See what I'm saying? So everything is cranked up an extra level. And so that's what makes the course challenging. The idea and what you're going to be doing and what it's all about, not necessarily so hard. This is the stuff that gets tricky. So you'll see, obviously, as we move on. Now, a little bit about what calculus is about, okay, like the big picture. I mean, calculus is a huge subject. There's Cal 1, there's Cal 2, Cal 3. I'm going to stick just with Cal 1 right now. Cal 1, or calculus in general, was, do you have space? Let's see. I know there's a chair over here. Okay, there you go. You need another set of notes there? Do we have any extras? That's extra. Here you go. Calculus was created by two people. They created calculus independently of each other, so they were different parts of the world. They created calculus at different parts of the world, but at about the same time. They didn't know of each other. That's Isaac Newton and Leibniz. So these are the fathers of calculus, which I think is pretty amazing. Newton, I mean, at that point in time, you go to college, you go to school, you learn math, right? At that point in time, PreCal, kind of the calculus trig stuff, was kind of the end of the road when it comes to math. There wasn't really a whole lot more. Of course, there was more math, but people had not been able to solve certain types of problems in math, and there was no class you could take for it. But the problem was still there. They were trying to figure things out, and they just couldn't. Newton and Leibniz created a way to solve these problems. And it's quite amazing. I mean, when you think about it, it's kind of like, think about you go to school, you learn all about this one subject, and you get to the end, and you're like, is there anything else? They're like, nope, that's it. That's it. You're at the end. And they said that's not enough. So they went back and on their own. Newton did it like in his backyard in his shed, basically, came up with calculus, and then took it out to the world. Now, Newton also did a lot of other stuff, laws of motion, astronomy stuff, and y'all have heard of Newton's laws of motion? Okay. So Newton has a lot more on his credential list than Leibniz does. And we'll talk a little bit later, especially if you take Cal 2, you'll see some of the major differences between their two calculuses. Newton gets more credit because Newton's calculus, the way he looked at it, was more powerful than Leibniz. There were problems that Leibniz got stuck on that he couldn't do, that Newton was like, those are easy, because he did it kind of a different way. So Leibniz, though, had great notation. Do you all know what I mean by notation? It's like when I write f of x, does everyone know I'm talking about a function of x? That's notation. The notation Leibniz used for calculus was very simplistic, and so a lot of people picked up on his notation real fast. Newton was a little bit, his notation was a little ugly and kind of left some windows open and gray area, and so people don't like his notation, but his calculus was much better. Does that make sense? I don't know if what I'm saying makes any sense or if it's even interesting to you at all, but calculus was born from this idea. Okay, think about this idea right here. I'm going to draw a graph here like this. I'm going to pick a point. I'm just going to call it x equals a. So I picked a value of x, and up here on the graph, there is some y coordinate, some y value, right? It would be f of a if this function is f. So what I'm saying is you plug a into the function, it spits out a value. The value is f of a. That make sense? All right. So if I gave you another point on this graph, let's say here, could you, because now you would have 2 points, wouldn't you? Couldn't you connect these with a line? Yes? And if you have 2 points, then you can find the equation of the line, and you can find the slope of the line, right? Yes? So far, not a big deal, right? Now, what if I take that point and move this point right here? What if I move it closer? I move it right here. Now the line connecting those would look like this, wouldn't it? I would have a completely different slope than the first one I found. And the slope, how do we define slope of a line? Do you all remember slope of a line? Rise over run, right? That's the basic idea, rise over run. And so if I move that point, again, the green one, even closer, that line would change, wouldn't it? It would look like that. Do y'all follow this? And what if I move it even closer? It would change a little bit more, right? And I get even closer and closer and closer. And it would change a little bit. But would you agree that it's moving towards something, it's getting closer to a certain line, but like, it looks like this one here, and it's starting to move up like that? and it's going to get to some place, and then it's not going to just jump, right? It's just going to be like that somewhere up there. What if I move that point, that second point, right on top of the first one? Can you have the equation of a line? What would your run be? It would be 0, wouldn't it? Because how far to left or right are you going if it's 2 points right on top of each other? You're not moving, right? So you would have division by 0. And what's wrong with division by 0? It's undefined, right? In our number system, you cannot divide by 0. But is it obvious to everyone that it looks like, again, as I moved that, it was getting closer and closer to something, right? It was getting closer to something. So can we still find it? And that's what Newton was able to do. He was able to find a way to get around that division by 0 and still come up with a numerical answer. That slope is approaching something, and he was able to figure out what it was. We're going to study this in depth, all right? But just that's to kind of motivate us a little bit. Another result of calculus is something like this. What's the area of a circle? We all know it's like pi r squared or something, right? Like we've heard that. But where does that come from? Where does that formula come from? So imagine if I had this circle. Could I draw like a rectangle inside of it like this? Could I measure the area of that rectangle? So I break out my ruler. I measure, length times width, right? I multiply, I get an area, and I can figure out what the area of that is, right? Would that be the area of the circle? No. So what I would do is I would maybe add another rectangle, and I'd go out there and I'd measure that, and I would figure out what that is. I add those two together. Is that the area of the circle? No. So I keep doing this, right? And I keep drawing my rectangles better and better and better, and smaller and smaller and smaller. I go measure, and the more rectangles I fit in here, right? The more I fit in, the closer my answer is. But am I ever going to get to the answer? No, I'll just get closer and closer, right? So that kind of sucked, that approach. So why don't we do this instead? Why don't I draw a rectangle, or a square in this case, outside? Can I find the area of that red rectangle, or that red square? Can I find that area? But that's too much, right? That's bigger than the area of the circle. So then I can come in and start subtracting smaller rectangles, can I? Yes? But no matter how many little rectangles I subtract, that'll still be more than the circle, won't it? So what I'm doing is the rectangles inside, I get a number that's smaller. The rectangles on the outside and subtracting, I get a number that's bigger. And the more rectangles I draw, I'm closing in on the real answer, right? Calculus allows us to have a way to do an infinite number of rectangles and figure out what happens if I go and let the number of rectangles be infinite. And therefore, you can get to the actual true only answer. You squeeze the answer between two numbers, and eventually they get down to pi. What's pi? Or pi r squared, but what's pi? 3.14, and it keeps repeating, non-repeating, right? Keeps repeating, non-repeating. Keeps going, right? Non-terminating, non-repeating decimal. So you can only get as accurate as how many decimals you go anyway. So you squeeze it between two numbers, you get as accurate as you want. I don't know if that makes sense. The big point here is calculus allows you to do something infinitely many times. In college algebra and PreCal and everything you've ever studied, it's always been do this, and you always do a couple of operations, and then it's over, right? Calculus is you do an operation, and you do it infinitely many times, and what happens? And you can get results like getting around the division by 0, or finding the area of something by adding up an infinite number of things. It's a completely different idea than anything we've done before. So it's like infinite processes is what we're looking at. All right. Before we can get to all that, though, we got to start with some structure and make sure we're all on the same page, and then we can start opening up these doors to different problems. Everyone has the notes? No questions? Okay, here we go. So the reason I do these notes is so that you don't have to write all this down, right? So you can we don't have to waste time with, okay, let me write down what is a function. You remember that? We can just talk through it. So a function is a rule that assigns to each element x in a set D exactly one element f of x in a set E. So a function is just a rule. In what we do in this class and everything we pretty much have done in our lives in math, a function is always taken a number in and spit some number out, like the function x squared, right? You take a number in, you square it, spits it out. So a function is just a machine. That's all it is. The domain of a function, right? The domain of the function, the set D, is the values of all the values, all the inputs of the function, the things that can be plugged in and evaluated. And then your range of the function is all the stuff that comes out. So if you take a function like x squared, right? If I take a function like x squared, what's the domain of this function? What are you allowed to plug in here? Okay, so everything, right? You're telling me there's no restriction on this function. This function can square, you can square anything. Doesn't matter what it is. You can always square it, right? So your domain, the set D, would be negative infinity to infinity. That's the notation that we could use. That's called interval notation. There's also set notation, which would look something like this. Oh, x is between negative infinity to infinity. Or you could use the good old double struck capital R, which is all real numbers, which they all three mean the same thing. So the domain of that function would be everything. What about the range? What are the outputs of this function? All positive numbers? Can you get 0? What about negative? Can you get negatives out of this, though? So remember, the x squared is the machine. You can plug anything in, but is it going to spit out everything? Can you get x squared to spit out negative 4? No. Not unless you plug in 2i, but, right? But that's an imaginary number, and this entire book, Cal 1, Cal 2, Cal 3, is all functions of real variables. In other words, we do not deal with imaginary numbers in calculus, period. You have to finish Cal 3 before you take a class called complex variables, and then they say, now we're allowed to use I. And then the whole game changes. But it's, you know, it's actually a good thing. But that's later on. So here, if we're saying the only things that can go in are numbers, real numbers, no i's are allowed, there's no way to get a negative out. Because when you square anything, it's going to stay positive. But my question was, can you get 0 out? Yeah, because you square 0, you get 0. Is 0 positive? No. Is it negative? No. It's like neither. Right? So what would we say for the range? I'll say, I think I used E, didn't I? No. Exactly what am I? And I said E. Yeah, E was my range. How would I say everything 0 and positive? How about 0 to infinity and a bracket on the 0? The bracket means 0 can come out of this, right? Or you could say in set x is just bigger than or equal to 0. Any number bigger than or equal to 0. All right. Whenever we talk about functions, we have this idea of what's called the independent variable and the dependent variable. The independent variable for us normally, most of the time, is x. That's the thing that gets plugged in. Then the thing that comes out, which is usually represented by f of x or the y, is called the dependent variable. See, because y depends on x, right? You tell me what x is first, and then I will tell you what y is. The x is called independent because it doesn't matter, right? It's independent, it's all by itself. Doesn't care what's happening. It comes through. Y is saying, I can't tell you what I am until you give me what x is. The importance of this concept is that later on, we will have independent variables that it's not x. And so we need to make sure that anytime we're working with something, we're very clear on what the independent variable is and what the dependent one is. We need to know that before we can start doing any calculus. Whoa. If at any point in time you have a question, let me know. All right, so what is the graph of a function? A graph is a visual representation of all of the inputs and all of the outputs. So a graph is just a way to visually understand what a function's doing, right? If I say, look, here's the x squared function. We can sit here and talk about what it does. Plug in 0, it spits out 0. Plug in 2, spits out 4. Plug in 3, it spits out 9. But we can do even better than that by drawing a picture of it, right? The picture helps us see, and we would see x squared as that parabola, right? So the graph is just a way of getting us, our brains, to see it. So here's an example of a function. F of x, y equals f of x is negative x cubed minus x squared. This is a third degree polynomial function. Third degree polynomial. So we could do old-fashioned graphing, right? Plug in values of x, evaluate the function, spits out values of y, and we could start plotting the points of the graph, right? If we plot a few points, we start to get some idea of what's happening, right? But how do we really get a good idea of what's happening? I mean, could you draw it just from this right here? You could try maybe, right? But if you put more points in the table, right, you make more points in your table, you get a better idea of what it looks like. You put 50 points in, you're having a real good idea of what this thing is doing, right? Put 100 points in, right? That's the graph. But it's just a visual representation of all those dots. And when you connect them all, it creates the curve, right? Make sure that you are aware that f of x is the height of the function's value, or the height of the function at the value x. So again, I'm going to use this and bring this in over here. Okay. Can you all see that okay? All right, so look what's happening here. For this particular function, which is drawn in red, if I plug in -4, it spits out what? It's hard to see here, right? But I have it right here. You plug in -4, it spits out 1.6. F of x is the function's height, which is 1.6. So the distance between here and here is 1.6. As I move along, the height's going up. There it's, what, 3.2. I know that's hard to see from in the back. And then I get here, I have 0, right? The height is 0. That's actually an x-intercept. And I keep going. Now I get, what, negative values for my y, my f of x. So, but it's still a height. We could look at it as a height, but negative would mean below. These 2 points right here, your function's value is positive, right? Your function's value is positive. These 2 points, your function's value is negative. This point, your function's value is 0. Can you tell me, I might be getting ahead of myself. Can you tell me from this picture where the function is positive? Where is this function positive? I want to know all x values where it's positive. So how could you say that? Wouldn't it be from here to here, right? From this point right here to this point right here, between those points we should say, right? Our function is always above the x-axis, so it's positive. How would you say that? Between there and there, but not including the endpoints. How would you say that? So I'm going to say f of x is greater than 0. That means the function is positive, right? On the interval, what was it, negative, was it 6 or 5? Come here. There we go. It looks like -5, doesn't it? From -5 to where? 0. Now I use parentheses instead of brackets, right? The parentheses mean do not include -5 and do not include 0. Why? Because what's happening at -5? What's the function's value? It's 0, not greater than 0, right? So I don't want to include that. Now, is that the only place that it was positive? It was also positive over here, wasn't it? To the right of what? Looks like 5 again. So to the right of 5 forever. It looks like from the picture it goes up and keeps going, right? So I would say that by saying from 5 to what's forever? Infinity, and then parenthesis like that. And how do I join two sets together? What symbol do I put between them? Union, right? And then we could do the same thing for negative, couldn't we? Where's the function negative? Negative infinity to, what was it, negative 5, right? And then union from 0 to 5. And just for the sake of doing it, where was the function 0? Yeah, if we go back to our picture, there were 3 places. It was 0 here, here, and here, right? 3 places. Now, when we say 3 places, we don't mean intervals, right? 3 exact values. So how do we say that? Well, we put the brace instead of the parentheses. So it would be negative 5, comma, 0, comma, 5. Sorry, the brace is terrible. So this means that the function is 0 at these 3 points, these 3 values of x. All right, vertical line test, y'all remember that? If you're looking at the graph of something, if you want to know if it's a function, it must pass the vertical line test. Now, this is where I was saying you have to know the difference between the independent variable and the dependent variable. Is this a function of x? So if this is our x-axis, a regular x-axis, a regular y-axis, if we're trying to see if y is a function of x, then we run through with the vertical line, right? And we say, do we hit it? Do we ever hit that graph more than one time? No, so that would pass the vertical line test, right? So it is a function. But if I change the function over to that, this is a parabola that opens sideways. Is this a function of x? Well, we come through with the vertical line. That's okay right there. It's okay if you don't hit anything. It's still okay if you don't hit something. It's still passing the vertical line test. It isn't until you actually hit it 2 times that it fails, right? So this is not a function of x, is it? Is it a function of y, though? That's a different question. If I say, now, I don't want to get too deep into this, but if we just kind of turn our heads and look at it sideways, now y, if we treat y like the independent variable and we say that x depends on it, then we run a vertical line test this way, would it pass? Yes. So that's not a function of x, but it is a function of y. More to come on that later. Piecewise functions. A function defined to be different functions on different ranges of the domain is a piecewise function. So the important thing about a piecewise function is that it can start off by doing something like acting like a parabola that's opening up, and then at some point you can switch it completely to a different function and make it be something else. And you can do this as many times as you want, but anytime you have functions that do that, they're called piecewise. Good examples of those, I know I've been paying just a ridiculous amount of money for electricity these last few months. Like with your electric bills, anyone who pays their own bills, you get, it's the same thing with water. They put you in different tiers. Like if you use a certain amount of electricity, you pay a certain amount. But once you go past a certain amount of electricity, you start paying more for it. And they have like different tier levels. And so if you get too high on the tier, you start paying a lot more for the electricity. So what that is a piecewise function. It's like it behaves a certain way, and then you get to this next tier, and it's like instead of it being like that, it's now like this. And then we get to the next tier, it's like that. And so it keeps changing as you go. That's what a piecewise function would be like. All right, now let's talk about a little more about this interval where it's positive, negative. We just did this, right, a second ago? Where a function is positive, that means the function's greater than 0 or above the x-axis. A function is negative when it's below the x-axis. A function is 0 when it's on the x-axis. So looking at this picture right here, We just did this a second ago, so I hope this is pretty clear now. Where is this function positive? This is negative 5. Negative 2 to 0, parentheses, right, no brackets, and then 2 to infinity, okay? Now, what I have here is I can just click on this and show where it's positive. Can't really tell in this classroom. It turned green there, right? And so this little interval here, and then from here on. So there's the answer right there. And then where it's negative is over here, which is all of this stuff, negative infinity all the way up to negative 2, and then from 0 to 2, right? Where is it 0? Those 3 points. Now we go to a slightly different concept. Right now we have the concept of positive and negative, which just means when are you above and when are you below the x-axis, right? When are you above, when are you below? Now we talk about increasing, decreasing, and constant. So when we look at a function, we normally read the function from left to right like we do a book, right? You go from left to right. When we say it's increasing, that means as you read from left to right, it's like you're going up a roller coaster, right? And then you get to some point, and then maybe you start coming down, then you're decreasing, right? If you ever flatten out, that's constant. That's what all this means, right? That's what that is saying. If I pick 2 points, right, where the x1 is less than x2, that means x1 is to the left of x2. Then f of x1 right here, if that one is lower than this one, then it's going up, isn't it? That's the more technical definition of increasing. But I just want us to understand it just more visually, right? Increasing like this, decreasing, and then constant. So note, what does it mean? Function increasing, decreasing, constant. So here's that same picture that I just showed you. If I have 2 values, x1, x2, this one is below this one, so it's increasing. So you can see as you move from left to right, you were going up, weren't you? Or if I connect those 2 points with an arrow, the arrow is pointed up. Decreasing function. So this point is to the left of this point, and then this point is above this one instead of the other way, and that means you're going down. Constant is like a flat line, right? There's no change in the function as you move from one point to the next. No change in the value. Now let's see if we can get the answers to this. Where is this function increasing? Increasing. I heard -2 to where? -1 from here to here? It was going up. Does it look like that to you? But what about over here? If I'm moving to the right, I'm coming up still, right? So it does appear that this is coming up, even though it looks kind of vertical. We have to imagine this graph keeps going down in this way, right? So if I'm, again, reading from the left to right like a book, I am coming up, coming up, coming up. I keep coming up until I get to this peak, right? And that peak, I don't know, does it look like it's happening at 1? Close enough, right? Right here. After I get past that point, what happens? I start going down, right? Decrease until I get to the bottom here, and then I increase. So I'm actually increasing to the left of what number? -1. So I would say from -infinity to -1. Now, I apologize, it's not -1. Looks like -1 kind of, right? It's actually -2/√3. But you would never know that by looking, right? So how in the world did I know it was -2/√3? How did I figure that out? No. I used calculus to figure that out. I used calculus to figure out exactly where that highest point is. And that's what you'll be able to do, just not yet. All right? And then down here, to figure out that this x value was positive 2/√3, we use calculus. Right now, we can't do it, but we'll be able to. Do you all understand the difference? Do you understand the difference between that picture and this one right here? Right? In this one, we were saying when's it above and below. The other one, we're saying when's it going up, when's it going down. That's totally different concepts. Going back here, so where is it decreasing? Just between here and here, right? It's the only place going down. So that little interval right there, which is this right here. Any questions on that? Sure? Y'all are excited? This is pretty exciting right now? Come on. They're in Canvas. Just what you see right there. I'm glad you brought that up. If you are interested, any computer science majors? Okay. If you are interested, how many of you have heard of a website called Wolfram Alpha? Wolfram Alpha? Not enough of you have heard of that, so I'm going to put it up here. Wolfram Alpha. Come on. We'll go take a look real quick. Here's Wolfram Alpha. Look, it's a shortcut. All right, what do I want to do? Let me just type in x squared minus 4. We did that earlier. Let's just see what Wolfram thinks of x squared minus 4. Well, it says if you want me to treat it like a graph, there's a graph of it. If you'd like me to factor it, I can factor it. If you want the roots, that's the roots. Here's the polynomial discriminant, which, what the hell does that mean, right? What's the domain? All real numbers. What's the range? What's its parity? It's even. What's the derivative? That's what you're going to be doing in this class. What's the antiderivative? That's Cal 2. What's the global max and min? That's what you'll be doing. Here's a definite integral on a closed. My God, Wolfram Alpha is almost. I mean, it's just too much information. Not too much, but there's so much here. You can do a lot with this system. So getting back to your question and this program right here that I'm showing you all this, and I'm able to move things around, all this stuff, is done using a program called Wolfram Mathematica, which is a program that I've been using since, geez, I don't know. I think they're on Mathematica. I think they're on 8.3 now. I started coding this when it was 4.1. So any computer science majors, like there's the code that I typed to make that happen right there. So if you are interested in being able to do what I'm doing in class right here, slide these things around, if you want to be able to do that, you can go to Wolfram's website and you can download a player. It's kind of like you know, when you want to read an Adobe PDF, you have to have the PDF reader. You can get a reader from their website, and then I can give you the files on a flash drive, and you will be able to do everything I'm doing here. If you're interested, but you have to come talk to me about that. What you're going to get online is just in our class files, just a PDF that you can print like this. You won't be able to slide things around. I took all the pictures out because it would take up too many pages. All right, let's move on. Let's say that we have a function, and a function is defined, and we're asked to find its domain, or what's called its implied domain. We know from our experience with functions that not every function behaves well. I mean, sometimes you plug in something to a function, it can't handle it, right? Can't take the square root of -1. If we're just dealing with real numbers, right? Can't take square root of -1. Can't divide by 0. So let's work through these examples right now. I'm going to work through them with you. I'd like for us to find the domains of these, and you can help me out here. Let's look at this first one. Okay. What issues could we possibly have here that we would be afraid of or be concerned with? having 0 in the bottom, right? Because we have a rational function or a fraction, right? We just got to make sure that thing's not 0. If that thing's 0, our function doesn't know what to do. So to find its domain, I'm going to go ask myself, well, when is that 0? And then make sure I throw those answers out, right? So I'm setting the denominator to 0. That's a quadratic equation, right? I would expect everyone in Cal 1 to be able to factor that. X plus 8 minus 1, right? And then what do? Set each to 0, right? Can someone shut that door, please? Thank you. Do we agree with that? Now, I need to talk about the domain, right? I can let x be anything except these two. So if you need to, you could draw a number line. Here's -8. We don't want that. Here's 1. We don't want that. We want everything between, everything to the left, everything to the right. So how do we say that? In interval notation, -infinity to -8. Oh, that's kind of cool. Then -8 to 1, and then 1 to infinity. So it's just this interval. We jump over -8, and then we jump over 1 and keep going. It would be those 3 intervals. Do you all understand that? Agree with that? Any questions on that? Has anyone heard what math dorks call infinity? Have you ever heard lazy 8? No. It's a lazy 8. See, there's 8. There's a lazy 8. It's, yeah, I didn't say it would be funny. I'm just saying that's what they call it sometimes. Lazy 8. So that's pretty clean, right? What if this was, I mean, just if I change that to a 9, you couldn't factor it, could you? Would I expect that you could still solve it? Absolutely. How? How would you solve that? Quadratic formula, complete the square, right? But I would expect you could do that. So the expectation, I guess what I'm saying is that in a Cal 1 class, I expect everybody could solve pretty much any quadratic equation, because you always have the quadratic formula, right? But if it factors, by all means, do that first. Let's look at the next one. G of x, x over square root 4x minus x squared. What issue do we have to deal with here? The square root, you cannot have a negative under there, right? That's number 1. Number 2, you can't have 0 on the bottom. So let's think about that. We need to be sure that this thing right here is always positive, right? Greater than 0, and what? It can't be 0 itself, right? So I could just say that. It has to be bigger than 0. That thing under there, what do we call that thing under the radical sign? What do we call the thing that's underneath the radical? The radicand, right? The radicand has to be positive. Yes? So what I'm going to do is I'm going to just write that down. I want to know when that radicand is positive. Now this is not a quadratic equation. What do we call this? Quadratic inequality. You all heard that before? Quadratic inequality. And there's a huge thing we have to be aware of here. When you have a quadratic inequality, you do not solve it the same way you solve a quadratic equation. You have to treat it differently because of the way things happen when things get squared. And you know, when you square two negatives, like when you square a negative, it's positive. Things get weird. So you can't just set this to 0 and then try and, well, you just can't do that. I don't want to get into the details. Let's approach it, though, the proper way. Here's what you would do. There's kind of 2 approaches, but you would come over here, a completely different sort of problem. You would say, okay, let me ask myself, when is it 0? Okay, I'm trying to figure out when it's bigger than 0, but let me first say, when is it 0? And you solve that. How would you solve that? Again, kind of a rhetorical question here. How would you solve this? Well, maybe factor an x out, right? Factor an x, and then set each of these factors to 0, right? So you set x to 0, you get there, and then you set 4 minus x equal to 0, and you get one answer is just x is 0, and the other answer is x is what? Careful. If you move that 4 to the other side, it's negative, but then you still have a negative x. So it'll be positive 4. So look, if x is 4, right, or 0, this thing is 0. You don't want that, right? You want to know when it's bigger than 0. So let's just look at it this way. I'm focusing all my attention on this. This. If I were to graph that, right? If I were to say, look, let's graph this. What is it? What does 4 minus x squared look like? Is it a line? It's a parabola, right? Which way does it open? Down. Why? Why does it open down? Because there's a negative in front of the highest power of x, right? So that opens down. Where does it hit the x-axis? When is it 0? At 0 and 4, we just figured that out, right? So what I know right now is that at 0 and at 4, this thing hits the x-axis, doesn't it? And I know it's a parabola that opens down, so I know it's got to look something like that, right? So now if I look at this and I ask myself, well, hey, when is it bigger than 0? I'm just saying, when is this graph positive? When is it above the x-axis? When is it above the x-axis? 0 to 4. See what I'm saying? Do I include 0 or not? Do I include 4 or not? If I include 0, it's going to make this thing 0, isn't it? And I want it to be strictly greater than 0. So my domain, I'm trying to get to my domain here finally. The domain of this function would be everything between 0 and 4, but not including 0 and 4. I hope that made sense. We're about halfway through class. Y'all feeling okay? Last one here. H of x is secant x. So now I'm going to tap into a little bit of your PreCal here. What's the domain of this function? Well, you have to remember what secant is, right? The definition of secant was secant of x was 1 over sine, cosine. What? Should I just flip a coin? That's cosine. All right. Let me see if Canvas is up yet. I doubt it. It's up? I still doubt it. I mean, I don't doubt that it's up when you just said that, but I doubt that it's going to be up when I type this in and try and log in. Well, I'm not there yet. Oh, wait, hold on. I just logged in. I just logged into ACES, and then I click on Courses, and then you should see listed here your Cal 1. This is what I'm teaching. So, where are you? You're 12, right? Yeah, section 12. Okay, there it is. All right, so I have the orientation video everyone has to watch, the syllabus, which I'm not going through. I do that in the video. The schedule, which is the layout, the day by day, blow by blow, what we're going to cover, what homework assignments are there. It's all there. You can print it out and put it somewhere. I say in the orientation video, this is suggested homework. This is never the homework you should do until I finish the class, because sometimes we don't get as far as what the problems say to do, so I have to like trim it off or something. So if you miss class, make sure you watch the video, see what I assigned. What else? Course videos, class lecture videos. What I'm doing right now, recording the screen, that is a class lecture video. The course videos are videos you're supposed to watch before you come to class. Again, watch the orientation, you'll understand what I'm saying. Files. This is where you go to get everything. So over here, you have the notes, course notes, what I handed out to you right there. There's chapter 1, chapter 2, chapter 3, chapter 4. Print those out. Class notes. You know how I'm writing this stuff down right now? I'm going to save that to a PDF, and you can print it out later. Come back. Formulas. That's the reason I came here was for the formulas. You need to download this formula sheet. You need to print it off, and I suggest you start bringing it to class. It's the last, I think, six or so pages that come in the book, these hard pages in the back. It's those pages, and they have a bunch of formulas that will become useful. You can use these. So here's secant. Wait, no. No, where is it? There it is, secant. Secant, 1 over cosine. So it might be good, if you don't remember all this, to have it out on your desk. So what is the domain of secant? Well, if it's 1 over cosine x, what we have to be concerned about is the possibility that that's 0, right? What if that's 0? So now you ask yourself, well, when is cosine x equal to 0? And now we get to discover how comfortable you are with the PreCal and how you were taught or how you approach a problem like this. In PreCal, this is known as a trigonometric equation. It's an equation with trig stuff, right? I'm asking you to tell me when that's 0. So what values of x do I plug in a cosine to get 0 to come out? Pi and what here? Pi and 2 pi? 0 and what? Pi over 2, 3 pi over 2. So how in the hell are we going to do this, right? This depends on you, all right? This depends on your comfort level with this stuff. There are 2 approaches that I think. One is completely graphical, coming from the graph of cosine. You have to know what it looks like. It's graph of cosine. Split it pi, 2 pi, pi over 2, 3 pi over 2. The places that it's 0 are here and here, right? Now, I agree. Pi over 2 and 3 pi over 2, that is correct. That's only, though, if you're looking between 0 and 2 pi, right? Because this graph actually goes backwards, right? Forever, and it goes this way forever, doesn't it? Both directions. So how many places is the cosine function actually 0? Infinitely many, right? Infinitely many. You cannot give us just 2 answers if there are infinitely many. We need a general answer, a general solution that covers all infinite answers. So those 2 aren't going to do it yet. But that would at least get you going, right? How many of you would think you would go about solving this by looking at the graph of cosine? Just trying to get a feel for the class here. How many of you, graph? Okay. How many of you when you look at trig functions, look at it more like, here's the unit circle, and corresponding to every point on the unit circle, there's some angle here, and then the x-coordinate is cosine of the angle, and this is sine of the angle. How many of you would do it that way? Yes. This is the best way to do it, okay? So when we say cosine of x is 0, all we're saying is where on the unit circle is your x-coordinate 0, right? Because cosine is the x-coordinate. So where is it happening? Here and here. Now, you do have to know what those angles are. Pi over 2 and 3 pi over 2. However, I could say this, right? Pi over 2. Then if I kept going, it would have been 3 pi over 2. But couldn't I have gone and come all the way back around to this, right? So the way that we get all the answers is as follows, or at least the way I would recommend you do it. To get this answer up here, I just need to turn by pi over 2. So I'm just going to put pi over 2. plus, now, how could I get to this one down here? I would just add another how much? How much would I have to rotate by to get from here down here? I'd have to add a pi to that, right? And then how would I get back up here? So I'm pointed down. How do I get back up there? Add another pi, right? And how do I get back down there? Add another pi. Add another pi. Or I could go counterclockwise, negative pi, negative pi, negative pi, negative pi. So the way we do it is we start with kind of an initial point, which is the pi over 2 that orients us first. And then from there, we just add pi rotations, right? Either direction, and we start knocking out all the answers. So what we put next to this is k pi, or you could put n pi. We usually let k and n usually mean the same thing. K is an integer. An integer means that k could be 0, 1, 2, 3, 4, 5, or, you know, forever, or you could say -1, -2, -3, -4. So k is an integer, n is an integer. Does that make sense? Okay. Did y'all remember that at all from PreCal? Finding general solutions for trig functions. When I teach PreCal face-to-face, this is one of the biggest things that I make sure students can do. Solve trig equations using the unit circle. Next thing. We need to actually say, what? Get this domain, right? Aren't we really saying x can't be these? Look, x can't be those? Because if x is those, right, then we have division by 0. So how in the world are we going to write that? Because don't you have an infinite number of intervals now? So instead of writing an infinite number of intervals, this is the cleanest way to write the domain. Instead of telling me what x can be, tell me what x can't be, because it's easier to do. So we want to say x cannot be pi over 2 plus k pi. That would be our domain. Questions, comments, concerns? Nope. And I'll even add to that, it doesn't matter, but I'll even add that you should be comfortable enough to do this also. So what did I do there? What did I do from here to here? I got a common denominator. So I just said put 2 here, which is really a 1. And since they have the same denominator, I can put them together, and then that gives me this. And you could even say that that's the same as, what, pi times 2n plus 1 over 2. So all I did here is factor the pi out, right? That left me with, when I pull a pi out of here, I get a 1. Pi out of here, I get 2n. What's nice about this notation? Just look at this for a second. What's good about that as opposed to this one? What I'm saying is compare this to this. Which, you know, what's the advantage? Okay, let me help. Start giving me answers here. Start giving me some examples of answers. So you would let n be 0, right? Start with n is 0. If n is 0, what do you get? Pi over 2. Okay, what if n is 1? In your head, you need to do pi over 2 plus pi. What's pi over 2 plus pi? 3 pi over 2. Now let n be 2. What's pi over 2 plus 2 pi? Then you have to actually start add those, right? It can get a little complicated because you're having to get a common denominator each time. Look at this one compared. What if n is 0? What do you get? Pi times 1? So you get pi over 2, don't you? What if n is 1? What do you get? 3 pi over 2. What if n is 2? 5 pi over 2. What if n is 3? 7 pi over 2. 9 pi over 2. See how quick you start getting the answers that way? So there's an advantage to having this over this, but they're the same damn thing, you know? All right. Example, determining a function. We're going to do these 3 problems. Express the area of a circle as a function of its diameter. Express the volume of a cube as a function of its surface area. Express the surface area of a sphere as a function of its volume. So what I'm going to do is I'm going to do the first one. And then I'm going to let you, as a class, work together. Maybe you'll meet a neighbor and y'all can, talk about it and compare answers. Let's just see where everyone is, all right? I do the first one, give you an idea of what it is we're trying to do, and then you try and do these. So express the area of a circle as a function of its diameter. I'm doing like the easy one, all right? I want to express the area of a circle as a function of its diameter. So watch the way I write this. A, the area of a circle, I would like that to be a function of its diameter. So I'm writing, instead of writing f of x, right, where I say, look, f is a function of x, here I'm saying the area of a circle needs to be a function of its diameter. So right now, if I were to tell you right now, I had a circle with radius 2. Could you tell me the area? If I give you the radius? Right? Pi r squared, right? So you would say pi times 2 squared. So you say 4 pi, right? So the formula that we have for the area of a circle, pi r squared, the area is a function of what? The radius, right? Well, sometimes we don't have the radius, we have the diameter. So instead of having your area in terms of radius, let's turn it into area in terms of diameter. So here's what I'll do. All I need to do is somehow replace r with something in terms of d. So what's the relationship between radius and diameter? The diameter is twice the radius, right? Or you could say that the radius is half the diameter. Agreed? Either way. So if I replace, using this equation here, if I replace r with 1/2 d and then square it, that's the same formula, replacing the r with half of the diameter. And then square it. What do you get when you square 1/2 d? Pi times, what's 1/2 squared? It was a good summer, wasn't it? It was a good summer. What's 1/2 squared? 1/2 times 1/2. 1/4 d squared, right? So your area is 1/4 pi d squared. That's the area. Do you understand that what I did is I wanted to come up with a new formula that gives you the area of a circle in terms of its diameter instead of the one that we always use, which is the area in terms of the radius. To do that, we had to find a connection between the radius and diameter, find that connection, replace that variable, and then go through and just rewrite the equation. Now, your turn to do the other two. Would like to express the volume of a cube as a function of its surface area. So right now, if you have a cube, right? A cube is like a square but three-dimensionally. All the sides are the same, aren't they? X, y, z, they're all the same. So you can say x, x, x. What's the volume of a cube if you know all the sides? It'd be length times width times height, right? So if you know the length of a side, you can tell me the volume. But that's not what I want. I want to be able to give you the cube's surface area. And then from that, you tell me the volume. Well, that's what you're going to work on. You see if you all can agree on the way to do that. At each little table, you all try and work it and see if you can get your own answer and see if you all agree. And then on the next one, I want you to express the surface area of a sphere. Does anyone know the equation for a surface area of a sphere? Who has the formulas? Anyone have their book? No? May not be able to do that one then. Here's a sphere. Jot this down real quick. You'll need it. Here's a sphere, three-dimensional sphere. The volume of a sphere is 4/3 pi r cubed. 4/3 pi r cubed. The area or surface area of a sphere is 4 pi r squared. Part of the lesson here is that just because you don't know the formula doesn't mean that you stop doing the problem. That means you would go reference your formula sheet, or you've got this great thing nowadays that you can do. Use what's that thing? The internet, right? Google, something like that. You heard of that? So if you're ever sitting there and you're doing a problem at home and you're like, I don't even know what that formula. Go look it up, right? Go look it up. Okay, going back to that problem. So I want to know what the surface area of the sphere is. You have a formula right there for surface area, right? What is it? 4 pi r something, right? That's in terms of radius, though. Someone gives you the radius, you know the surface area. I want to be able to hand you the volume of the sphere, and you tell me what its surface area is. Right? Let's work on this in groups. I want you to kind of like break out of your little shell and get to meet people and do all that fun stuff. Talk to each other, and I'll give you, let's just see. I'll kind of walk around, and when I think it's time, we'll talk about them. We'll work through them. That'll be the last thing we do today. Make a friend. And coming to my office is such a great thing, because then you can work, and when you're all stuck, you send your representative to come figure out, what you do, and then I help you out, right? Okay, so we are going to work the cube problem. So the most important thing, I think, in the beginning was to understand that we are dealing with a cube. If you have a cube, all the lengths of all the sides are the same. That's implied by the wording of cube. So if we call every side x, x, and x, then the volume would be, and again, you would have to know that the volume of any, what do they call a rectangular box? It's like they call it a parallel pipette. It's this weird technical name, but what is called a rectangular box? If you have a rectangular box, the volume is length times width times height. But in this case, since length, width, and height are all the same, it's x times x times x, which is x cubed. All right, so that's what we know so far. We know the volume in terms of x. That's not what we want. We want volume in terms of area. So now you have to talk about the area. Well, what do we know about the area? I know that the area of just this front edge, if I were to look at that as its own problem, this is x, the area in here would be x squared, wouldn't it? But because a cube has 6 sides to it, each one of those sides is going to have an area of x squared. So we add them up, 6 of them, we get 6x squared. And now here comes the most important part. If I want my volume to be in terms of A, then that means I need to go into this equation that I have for volume. I need to replace the x with something that has a's instead. And the only thing I know about the relationship between x and a is that. I know that area must be 6x squared. So if I take that equation and I solve it for x, I can replace the x in yellow with whatever I get here. So to solve that for x, I divide both sides by 6. I'm working with this equation. I'm going to say 1/6 a. Is that all right? Instead of a over 6 equals x squared. And then how do I get x by itself? Square root of both sides. Now, anytime you take the square root on both sides of an equation, technically you're supposed to do plus or minus, aren't you? Why am I not going to worry about the minus? That's right. X is the length of the side of a cube. It's not negative, so I'm just not even concern myself with it. That's what x is, right? So now I say, all right, if I know what x is, I can go back into this equation up here. I can replace my x, just the x. It still needs to be cubed, but I need to replace it with square root 1/6 a, or a over 6. And then you could say even from here that this is 1/6 a to the 3/2. Because, why? Taking the square root of something is the same as raising it to the what? 1/2. So this technically is actually 1/6 a to the 1/2. That means square root, but then all of that cubed, right? So when you take something to a power and then raise it to another power, what do you do to the powers? Multiply them. 1/2 of 3 is 3/2. So you get that. So now what we have is an equation, a formula, where if you give me the area of the cube, right, I don't need to go figure anything else out. I just need to compute this, and I'll be able to tell you the volume. All right? Now, it's hard for you to imagine right now why it is we need this. But what's going to be happening later is, since I'm really running low on time, let me see if I can show you this. Uh-oh. Oh, man, where is it? I need to see chapter. Related rates, 2.7. Try and give you an idea of where we're headed with this. Holy crap. Here we go. Okay, you ready? Check this out. Now, this is not the cube problem. This is a different one. But okay, what we have is we're blowing up a balloon, all right? It's starting to expand, right? And if you've ever blown up a balloon, or you've ever, with your mouth blown up a balloon, at the beginning, right, you start blowing it, and it starts getting big pretty quick, right? But then as it gets bigger, you keep blowing, and it doesn't get as big as fast, right? Because it takes more air to get it to be a little bit bigger. So what's happening here is that in the beginning it's fast, right? It's growing fast, and then it slows down. See, look how it got real big, and then now it's taking longer for that to happen, right? So the question we will ask ourselves, and this is going to sound really strange, is that if I'm pumping air in at a constant rate, so it just keeps, I'm sitting there with the compressor, and I'm just blowing this up, air is going in, at a specific instant in time. So like right there, right at that instant, I want you to tell me exactly how fast the surface area was changing, which is a really weird concept. It's not saying, what I'm not saying is this. I'm not saying pause it, stop everything, and just go measure the surface area. It's not what I'm asking you to do, because anyone could do that. If I give you the radius, you could go find the surface area. We're talking about instantaneous rates of change. I'm saying at a specific instant, tell me how fast it's changing. In the beginning, isn't it really, the surface area is really increasing fast? But then as time goes on, the surface area is not increasing as fast. So to make that connection between the surface area and the volume, you first have to come up with an equation that connects the surface area and volume together, or else you can't do any calculus. So this exercise here is just getting us used to taking two physical things that we might have an equation for, and then using various equations to connect the two together in different ways. All right? That's that. But we're headed somewhere completely different that you would have never predicted from that. Let me see what else I've got here. Here's another one. A plane flies overhead, right? So a plane is flying overhead. Here's you. You're looking at it, right? You're looking at it. You're watching it go over, right? Well, let me do it this way. I'm watching the plane. Here it comes. My head's rotating, right? When it's way out there, my head's not rotating as fast. But when it comes overhead, I have to keep up with it. I got to rotate faster, don't I? So what we ask ourselves. Let me pause this one. There we go. Yeah, here. This one's a little bit better. Notice the angle. It's not, then real quick, see how quickly it goes from here to here? In the beginning, it's growing slow, and all of a sudden, and then it goes pretty fast, doesn't it? What we're going to say is right there, at that instant, right when I snap my fingers, how quickly was it rotating at that instant? So if you want to shoot this down and you're tracking it, right, the computer is going to say, okay, I know how quickly I'm rotating. I can be able to predict later where it's going to be. I mean, there's all these applications for it, but you have to be able to compute instantaneous velocities. Well, the only way to do a problem like this with calculus is to be able to somehow connect that angle to all the other given information, which means you'll have like a triangle and you're dealing with trig functions, and I hope that kind of opens up where we're headed, but this is the kind of basic stuff behind it. What was the last one that we were supposed to do? Surface. Let's make that a take-home quiz to be turned in first thing when I see you on Wednesday, is to finish off 1.19, express the surface area of a sphere as a function of its volume. You can work together on this quiz, okay? I don't mind if you help each other out outside of class, that's fine. What I ask you don't do, let's be very clear on this. Everything I pretty much am going to give you this semester, it's take home. I don't care if you work together. What you cannot do is go to the tutoring lab and sit down and just get a tutor to show you how to do it. That's not the point. All right? So if I start talking to the tutors, because I talk to them, they say, yeah, I have your calculus students are coming in, they're getting help on this. Then I make the quizzes in class, just you, and we don't want that, right? So everyone understand? First thing, everyone turns in their own copy or answer to this. Yes, ma'am? What's that? Homework. Is it not on there? Yeah, it is. Let me tell you what you can do, what you can't do. My office hours, just so you know, I usually after class will go to my office right after this for an hour, but not today. Today I have to pick up my daughter from her first day at school, so I will not be able to do that. I apologize, but from here on out, I'll be okay. Let me just make sure there's nothing on here I don't want you doing. Okay, you ready? Skip 20. So I'm going to tell you which ones to not do, okay? Don't do 20 or 20. Oh man, maybe I should do this a different way. Let me write down what I want you to do, because there's too many I'm taking off. You can do 2, 3, 4. This is off of page 8. 2, 3, 4. 25, 27, 28, 47, 48, 51. These last three are very similar to what you're doing right now. Just do those problems. I do not pick them up, right? Remember, I said don't pick them up, but you should always have those done by the time we meet again. Everyone have a great day. I do not pick up homework. But I would warn you not to not do it. Yeah.